All right, welcome back to PreCalc. Today we're going to start talking over section 8.6. There's quite a few different topics and ideas in this section, so probably end up breaking this maybe into two videos just to make it a little bit easier on everybody. There's going to be several formulas, so make sure you have your notebook out so that you can get the formulas down. But the concept that we're going to be talking about in this section sounds very, very, very easy. What we're going to be talking about is counting. All right, counting sounds like something we would have done as a preschooler or a kindergartner, but we continue to count as we get older and as we get into more advanced subjects. There's actually a branch of mathematics that's dedicated to counting and the probability that goes along with it, and that's an area of math called combinatorics. So some of you might be, at some point, you might touch on combinatorics when you go to university or go to college somewhere. Now we're going to have quite a few tools that help us with our counting problems. And the first tool is going to be called the fundamental counting principle. It looks relatively complicated, but it's much, much easier than it appears. What we have are these multiple events that are going to be going on. So event number 1, event number 2, event number 3, and so on that are going to be happening. And each of these events can occur in a different number of ways. Event 1 can occur in A ways. Event 2, that I called E2, can occur in B ways. Event number 3, that I called E3, can occur in C ways. And then the ellipsis, the ... says that you can continue that pattern for as long as you need to or want to. But then the conclusion, the then when you put all of the events together, so plural, when you put all of the events together, then they can occur in A times B times C times, and again the pattern would continue indefinitely. What we do then is multiply the number of ways in which these events can occur to get the total number of ways that all of the events can occur all together. Okay, and so let's look at some examples of how this fundamental counting principle works. And we'll start with license plates. We'll start with license plates in Minnesota from the 1970s. In the 1970s, the format for a passenger vehicle's license plate was 2 letters followed by 4 numbers. Okay, and if anyone's interested, for whatever reason, I can remember my mom and dad's license plate number from the 1970s. Their license plate was GW3232. Okay, but that was the format, 2 letters followed by 4 numbers. Now my question to you guys is, can you count up all of the number of ways in which Minnesota could create license plates back in the 1970s? The idea is, how many different letters could Minnesota have placed in this first position? Or our alphabet has 26 letters to choose from, so they'd have 26 ways in which they could select the first character. How many letters could be in the second position on the license plate? Well, again, there's 26 letters to choose from, so you'd have 26 ways to do that. Now, each of the next 4 characters are numbers, and how many numbers do we have to pick from? Please be careful not to say 9, because 0 is also an option. So 0 through 9, 0 through 9, 0 through 9, and 0 through 9. So we have 10 options, 10 options, 10 options, and 10 options for the 4 numbers. Now what the fundamental counting principle says is, if you have 26 ways you can pick the first letter, 26 ways you can pick the second letter, and then 10 ways in which you can pick each of the numbers, we multiply those together to get the total number of possible license plates that the state of Minnesota could create. And back in the 1970s, they could then create 6,760,000 license plates. That's how many they could create if there was no restrictions, if they didn't have any rules as to which letter combinations or number combinations that you could use. If there was no restrictions, 6,760,000. Now, they very well might not have allowed a license plate that would look like 00000. They might have thought that was kind of dorky. So they might not have allowed certain ones, but without restriction, that's how many license plates are possible. Now, in the 2020s, For passenger vehicles, we actually have different combinations that are possible. But one of the possibilities that we can choose from in the state of Minnesota now is to choose 3 letters followed by 3 numbers. Okay? Why did the state of Minnesota switch? Because we ran out of the 6,760,000 license plates, maybe minus any restrictions that were placed upon it. Okay? So now with one of our new formats, how many choices do we have? Well, there's 26 possibilities for the first letter, 26 possibilities for the second letter, 26 possibilities for the third letter, and then 10, 10, and 10 possibilities for each of the numbers. And the fundamental counting principle says you multiply those together to get the total number of possibles. So here there'd be 17,576,000 possible license plates in the state of Minnesota with that format. Now some of you might well have license plates where they've reversed the 3 numbers and the 3 letters. They put the 3 numbers first and the 3 letters second. Well, that means the state of Minnesota would have 17,576,000 more license plates that they could produce. I believe right now Michigan, if I remember this correctly, you guys could double check me, but I think Michigan now has 3 letters followed by 4 numbers, if I remember that correctly. All right, and in a license plate situation like that, they would actually have 175,760,000 possible license plates they could create. Okay? So you can think of any possible scenario you want. You could look at the different states and the different arrangements that states have, from California to New York to wherever you want to look, Ohio. You could look at all of the different license plate combinations. And if the next time you walk into the license plate office down on Chapman Street, look at some of the old license plates on the wall and think to yourself how many combinations were possible. Now we can actually use this for all kinds of other problems as well. As an example, if anybody's cell phone your cell phone number has the prefix 235, how many possible phone numbers could be created with that prefix? Well, if there's no restrictions, we would have 10 choices for each of the last 4 numbers in your phone number, and the fundamental counting principle would then say that you'd have 10,000 possible phone numbers that you could create out of the 235 prefix. Of course, there's probably restrictions. I'm not sure if they allow anybody to have the phone number 235-0000. I'm not sure if they use that one or not. And they probably stay away from anything that looks even close to 911. They probably don't let anybody have the phone number 0911, just to keep people from getting mixed up with that. Okay, here's another one. I just took a picture of somebody's lock out in the hallway. And the downstairs lockers have combination locks with 50 characters on them. You can see this one goes from 0 up through 49. Okay, so that means there's 50 options for each of the numbers. So how many locker combinations could you guys possibly have? Well, if you have 50 possibilities for your first digit, 50 for your second digit, and 50 for your third digit, then it's going to be, the fundamental counting principle says, multiply those together, and you would then have 125,000 possible locker combinations using a 50 number dial. All right, so if you forgot your combination and you came back and you just started guessing, you'd have many, many, many combinations to possibly choose from. Okay, if I gave you a group of letters and asked you to create different words, even if they didn't make any sense or weren't in the dictionary, from the letters in the word math, how many combinations of words could we create? Well, if you think about the word created as having 4 letters, how many different digits could be in this first position? Well, the answer would be 4. Well, once we use one of them up, let's say we used up the T, now how many digits could be in the second position? Well, we no longer can use the T, so there would now be 3. Once we've used up the M, now how many digits are left for the third position? Just 2. And similarly, once we've used up the A as an example, then there's only 1 digit left to put in that 4th position. And the fundamental counting principle would say then that you'd have 4 times 3 times 2 times 1, or 24 possible words. And again, I know they don't all make sense or anything, but 24 possible words that you could create out of those letters. Okay? Now, there's some notation that you're already familiar with that helps us with counting problems. And the notation I'm referring to is the factorial notation that we reintroduced everybody to back in section 1. And just a quick reminder to make sure everyone's okay on this. Factorial notation, again, by definition, n factorial is by definition, you start at n, and then you multiply by every number one smaller until you get down to 1. So n factorial is n times n minus 1 times n minus 2 times dot, 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 all the way down until you get to 1. So as an example, 5 factorial, start at 5, multiply by a number one smaller, one smaller, one smaller until you get down to 1. And in this case, that would be equal to 120. Okay? But that notation also helps us arrange or count the number of arrangements of things, especially when there's no kind of restriction on anything. As an example, what if we were to, one day in class when we're all back in class here in room 8, what if we were to start lining people up at the door? What if we picked 3 people? How many ways could 3 people line up at the door? The answer becomes, well, it's going to be 3 factorial, because whoever I choose first would have 3 positions to choose from at the door. Do they want to be the first person, second person, third person? The second person would only have 2 choices. The third person would be stuck with whatever's left, so there'd be 6 ways for that to happen. Okay? As an example, if there was 8 people, then the number of ways we could arrange you is 8 times 7 times 6 times 4 times 3 times 2 times 1, or 8 factorial. And if I remember that one correctly, I think I'm going to check it with my calculator. 40,320? Yep. So this one would be 40,320. All right? Or maybe we take everybody in class. We have 19 people in class. If we took everybody in class and counted how many ways they could line up at the door, well, the first person, let's say Margaret, I said, Margaret, go pick a spot over by the door. Margaret would have 19 spots to choose from. She could be anywhere from the first person to the second person, all the way down to the 19th person. And then the next person, maybe Amelia, would have 18 choices. Abigail would have 17 choices, and so on, until we get down to the last person, whoever we want to stick as last, I guess, if I'm going down rows. Sorry, Jonah, you'd be last there. Sorry about that. And then the number of ways in which 19 people could line up at the door is pretty darn large. My calculator actually can't quite handle that, but I'll give you as many decimal places as I have. 6451004. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. All right, so there'd be that many ways. That many ways for all 19 of us to line up at the door. All right, and so what would that be? Let's see, thousands, millions, billions, trillions. So it'd be 121,645 trillions, 100 billion, 400 million and change ways in which 19 of us could line up at the door. Okay? Alrighty. Now, we don't always want to use everybody in a class to line up at a door, or we don't always want to arrange in order everybody in a group. Sometimes we just want to select, maybe from our class, we just want to select a smaller group and arrange them. And when we want to select a smaller group, we call that a permutation. And I need just a real short definition so that you have something to compare to later. Permutation is an ordered arrangement. And the important word is ordered. When we get to our next definition, we'll talk about things that are not ordered. But a permutation is ordered. All right, and we're going to have a formula for permutations. We use a capital P, which, all right, shouldn't be a big surprise for permutation. And then we use 2 subscripts. The first subscript is traditionally n, and the second subscript is traditionally R. N represents the total number of objects, whether we're taking people or letters, or one of the problems we'll do in a little while is baseball players. And R represents how many at a time we're going to be selecting. Okay, so there's going to be a formula for this, and I need you to jot it down. So the number of permutations of n total objects selected R at a time is going to be n factorial divided by n minus R factorial. Okay? Now I do want to point out that you guys have the ability to find an NPR function on your calculator. What you'd have to do for everybody who has a TI is select Math, then arrow over until you get to the heading that says PRB, which is short for probability. And then I think it's the second option down, I believe, has an NPR attached. Or, I'm sorry, I should say, on the drop-down menu, NPR is probably, I think, the second option down below. Second option down below. So try that, Math, arrow over to PRB, and then arrow down to NPR. Now, if you just want to practice to make sure you can do one of these correctly, so just a simple numerical example. What if we had 8p5? Using the formula, that would be equal to 8 factorial over 8 minus 5 factorial. And of course, we would do what's inside parentheses. First, 8 minus 5 is 3 factorial. And then 8 factorial divided by 3 factorial should give us 6,720. Now, if you want to try the calculator method, what you'd have to do is enter 8 into your screen, into a basic calculating window, then find the NPR key under your math menu, and then once you hit NPR, it'll come back to the calculating screen and you have to put in 5, and then you'll just find the button on your calculator for equals or enter, equals or enter, and it should spit out then 6,720. So from now on, whenever we need to do a permutation or any of the future formulas, feel free to use the function on your calculator or the formula that I give you in class. Okay, but now just an application or two for a permutation. As an example, what if we take the junior class and I wish you guys were here so you could tell me how many people are in your class, but let's just make up a number. Let's say there's 35 people in your class. I don't know if that's low or high, but let's just take 35. And in the spring, we normally elect officers for every grade. Okay? And I'm just winging this, but I think we usually elect a president, a vice president, a treasurer, and a secretary to keep track of all the minutes. Okay? Well, my question to you guys would be, well, from your 35 people in your junior class, how many ways can we select a president, vice president, treasurer, and secretary? And the answer is, that's going to be a permutation of 35 total people selected 4 at a time. And the reason it's a permutation is the order matters, because the president has different duties than the vice president, who has different duties than the treasurer, who has different duties than the secretary. So it matters who is first, second, third, fourth, all right? And so the formula would say that this is then going to be 35 factorial divided by the difference, 35 minus 4 factorial. 35 minus 4, of course, is 31. And again, either do it by the formula or use the NPR function on your calculator, just totally up to you. And what we should get then is 1,256,640. Meaning, from your class of 35, there would be 1,256,640 ways to elect a president, vice president, treasurer, and secretary. There'd be that many ways in which it could occur. Okay? And another example that I'd like to do to finish off maybe the first half of this section. So the last example is I'm going to look at a baseball team. Okay? I'm not sure if we'll get to have baseball this season. I'm not sure if we'll have track or anything else this spring. I hope so. But let's just pretend we have a baseball team. And let's say that Mr. Ivancic on his varsity baseball team has maybe, let's say, 14 players. Not actually sure how many Mr. Ivancic would normally have on the varsity level, but let's say it's 14. Now, at the start of every game, Mr. Ivancic has to submit what's called a batting lineup to the umpires. And the batting lineup consists of 9 players in a list from 1 through 9, which shows the order in which they're going to bat. All right? Which shows the order in which they're going to bat. So my question would be, how many different batting lineups could Mr. Ivancic potentially submit to the umpire? Well, because it's important who bats first, second, third, fourth, and all the way down to 9th, it's going to be the number of permutations of the total number of players on the team selected 9 at a time, which means it would be 14 factorial divided by the difference, 14 minus 9 factorial. And so this would then become 14 factorial over 5 factorial, and it's a lot bigger than you think. So 14, whoops, sorry, hit the wrong button there. 14 factorial divided by 5, nope, I hit the wrong number again, doggone it, Omerza. Divided by 5 would then give me, let's see, 726,485,760. So with 14 players on a varsity team, Mr. Ivancic could submit 726,485,760 different batting lineups. Okay? So why don't we pause here? Let's stop this video so that everybody could have a break. And then please come back for the second half of this video. We'll have a couple more formulas and a few more examples. The second video won't be as long as this one. It'll be a little bit shorter. Okay, but let's take a break and then come back after a little Diet Mountain Dew or a little bit of water.